Okay, so from the beginning, here is my egregiously late and long overdue final physics presentation for Bradley Hughes, and I'm going to do this extended presentation on chaos, building on what I did for my last presentation. And so here we go. So last presentation I analyzed the double pendulum. So one mass on the end of a string attached to another mass at the end of a string, and we used Lagrangians to come up with this expression for its equation of motion. And then this can't be solved analytically. I have to do it numerically. And when you solve that numerically and plot its behavior for a bunch of initial conditions or initial displacements of theta 1 or theta 2, or theta 1 and theta 2, you come up with some very interesting behavior. And so last time, the point I tried to make was that for any infinitesimally small change in initial parameters, the behavior of the pendulum as time goes on is radically different and deviates hugely from the behavior down the road of initial conditions that are even slightly different. And so say we had an initial displacement of say maybe 12.2 degrees, and then we were holding the pendulum there, the theta 2 there, and we let it go, and it would do some kind of arbitrary chaotic behavior before settling down to a small sinusoidal for small amplitudes and then dying out. And then say again we did another take, and let's change my color here. We did another take at 12.3 degrees, which is slightly different, slightly initial parameter, slightly different initial parameter, slightly different initial displacement. And we let it go from here, and originally it would follow the path slightly, but then it would start to deviate, and the deviations would get bigger, and eventually the motion looked nothing at all like it before settling back down to a sinusoid function and dying off. And the big point was that these transient effects here for the oscillator were vastly different depending on the initial conditions. So even though this was a tiny difference here in initial displacement, by the time it got midway or a couple periods into the transient phase of the oscillation, the motions were hugely different, big difference, couldn't really tell them apart. Or you could very much tell them apart, even though it was the exact same system, obeying the same deterministic properties. And I just kind of covered that very vaguely in the last presentation, and didn't really delve into numerical solutions to this or show this really qualitatively or quantitatively, I guess. And this behavior, and there's a couple reasons for that. One was that even though the double pendulum is a very simple system, it's not quite simple enough to really be able to appreciate or really notice. I mean, this transitory effect with the double pendulum just looks, like chaos, because it is chaos, but we can't really just kind of right from the graph or from watching its behavior see any kind of rich patterns or interesting intrinsic behavior that is inherent to chaotic systems, even from this very simple system. So to really be able to appreciate kind of the richness of chaotic motion and the predictability that arises from its seemingly unpredictable behavior, we are going to analyze an even simpler system. And that simpler system is the damped-driven pendulum. And so this is one of the absolute simplest systems that exhibits chaotic behavior for certain initial parameters. And this is the system I'm going to use to kind of explore some of the interesting features of chaotic behavior in chaotic systems. And so first things first, I think I'm going to find an equation of motion for the system. And I'm going to do it not with Lagrangians this time, but just old-fashioned Newton's laws, except this time the rotational version of Newton's laws. And so we're going to have an angle here, phi, and because it's a driven oscillator, we're going to have an Ft as a driving force, and we're going to have a resistive force, Bv, and then we're going to have mg, force of gravity. And just for fun, I'm going to do this in rotational version of Newton's laws. So we have the moment of inertia times rotational acceleration is equal to total torque around the axis. And we're going to pick the axis to be there because it's the simplest and makes the most sense. And for this system, the moment of inertia for a bob in the end of the string is simply I equals ml squared. And then for our forces, we have BV. Well, BV is the magnitude of the restorative force. And so the torque due to BV is going to be negative BL squared theta hat. Yeah, because this is negative L BV. And this is going to be the magnitude of the force. And then the torque due to the weight on the end of the bob is going to be negative mg L sine theta from the diagram, sine phi. And the driving force, F naught of t, is just going to be the driving force. And we're going to let this be a purely sinusoidal force of F naught equals cos omega t, where omega here is the drive frequency, and this is the drive amplitude. Drive frequency and drive amplitude. Alright, and now we can rearrange our equation into something that looks a little bit like this. We have ml phi double dot equals negative bl squared phi dot minus mgl sine phi plus lf of t, and substitute lf of t, and we get ml squared phi double dot equals negative bl squared phi dot minus mgl sine phi plus lf plus lf naught cos omega t. And now we can simplify this a little bit and divide through by ml squared. And if we do that, we end up, we're going to divide through by ml squared and rearrange a little bit. And I'm going to end up with phi double dot plus b over m phi dot plus g over l sine phi equals f naught over ml cos omega t. And I'll just bring up another page here. And so, yeah, we're going to read it since, I'm just going to bring back what we had. So we had phi double dot plus b over m phi dot plus g over l sine phi equals f over ml cos omega t. And well, we can simplify this a little bit further, and with all of these things, give these some values. When we did our chapter on oscillations, we gave b over m the value 2b, or 2 beta I should say, where beta is the natural frequency of the system. Natural freak. And we can call... Oh, sorry, that's not true at all. Big lie. B is the damping constant. Damping constant. And G over L is what we're going to call omega squared, and this is our natural frequency. Natural frequency, so G over L is our natural frequency squared. Frequency. And lastly, we're going to come up with a new parameter called lambda. It's going to be dimensionless, and it's going to be equal to F naught over ML omega naught squared. So equals F naught over mg. And we're going to call this the drive strength. Drive strength. And like I said, it's dimensionless. And it's going to be a convenient way of basically modulating the drive strength parameter, because this is simply the ratio of the driving force to the weight. And so when lambda is smaller than 1, the drive force is less than the weight, and we can expect that the natural frequency will be, the drive force is less than the weight, and we're going to expect all of our amplitudes of oscillation to be very, very small. And if lambda is larger than 1, it's going to be a strong drive frequency, and we can expect that our amplitudes of displacement are going to get very large. And so we put all these substitutions in, and we end up with phi double dot equals 2... Oh, sorry, that's not right at all. And we end up with phi double dot plus 2 beta phi dot plus omega naught squared sine phi equals omega, or lambda omega naught squared cos of omega t. And this is the equation we're going to be using to explore some of the richness of chaotic behavior in chaotic systems. And so, since I'm posting these to YouTube, I think YouTube gives a limit on what I can upload lengthwise, so this might have to get broken into a few different sections. But next